So, good morning, good afternoon, good evening, depends on where you are in the world. So, we are here today for a new CASS talk. So, today with Professor Antônio Carlos Schneider Beck Filho from Federal University of Rio Grande do Sul, Brazil, talking about from silicon to cloud, paving the AI path with powerful hardware. So, before giving the floor to Antonio, just some few announcements. So if you lost some of the talks that are being done since 2022, there is about 150 talks available in this YouTube channel that you can see some fantastic talks available for free. So also some industrial talks are available. Next week we have in the region here the Microelectronics School and the South Symposium Microelectronics, where to be celebrated 40 years of the symposium and 25 years of the Microelectronics School. You can go to the web page to see the program that is already published there. Today is the deadline for the LASCAS 2025. To the number of papers we received till now, it will be one of the editions with a large number of papers, but you still have it till today. But I heard that the website will be open till tomorrow. So if you are finished your paper, you still have time to do the submission. And as you should know, as a flagship conference of IEEE Sequencing Systems Society, there is a selection of papers to be available submitted in TCAS2. And the ones selected for TCAS2 are published in the edition of the months of the conference. And then during the conference, there is an extra selection of papers to be invited to publish extended versions in TCAS1 in a special issue. So this is a great opportunity to have also a paper in a top journal of IEEE. In parallel to LASCAS, there is also the Iberchip, is the 31 edition of the workshop, so celebrating 30 years. And the deadline for the Iberchip is October 11, the extended deadline. Next year, LASCAS will be in Peru, in Arequipa, a nice location also. And in 2027, it will be in Panama City. If you are a member of CASS, you should have received the call to send the proposals to host LASCAS 2028. And end of April next year, we have the first edition of the Latin Conference on Internet of Things. So this is sponsored by the IEEE IoT technical community as a flagship conference. And the IoT technical community is composed and supported by 12 IEEE societies. CASS is one of them. The deadline will be in November this year. Then next year, we have a new edition of SBCCI that will be in Manaus. So Chip in the Jungle is back to Manaus after 25 years. So you have till March to submit your papers to the SBCCI. That is also sponsored by Sequencing Systems Society. But today we are here to attend the talk by Professor Antônio Carlos Schneider Beck Filho. So Antônio Carlos graduated in computer science from the Federal University of Santa Maria in the center of the state of Rio Grande do Sul in 2002. He holds a master's degree in 2004 and a PhD in 2008 in computer science from the Federal University of Rio Grande do Sul with a research internship at TU Delft in Netherlands, where he was also a visiting researcher in 2015. Currently, he is an associate professor at the Institute of Informatics of the UFRGS and contributes to 2 graduate programs, the computer graduate program and the microelectronics one. His research interests include reconfigurable systems, computer architectures, multi-core processing, and AI hardware. He has authored over 150 articles in international conferences and journals with extensive international and local collaboration, and he has published 3 books. For more information, you can look at his webpage that is stated here. So thank you again, Antonio, to accept our invitation. And the floor is with you to start your talk.
Thank you very much, Professor Hayes. First of all, I'd like to also thank CASS for inviting me for this talk. This is a shortened version of my tutorial that I gave during the last SBCCI, and I reinforced the invitation that Professor Hayes gave us right now for these great conferences. So the title of this talk is From Silicon to Cloud, Paving the A Path with Powerful Hardware. So it's more like a presentation with questions, more with questions than with answers, right? So some years ago, we worked really, really hard. And you can see here that we could increase the performance in following the Moore's law, right? So here is the processors. So until 2003, it was really all right to work, really working really hard. We got to be tired between 2003 and in this 10 years interval here, but it was all right. But you had to involve the programmers because you had to migrate to multi-cores. And there is an explanation for that. You see here, during these years, we still had a good amount of increase of transistors in transistors count. But because of thermal issues, power issues, we had to stop increasing the operating frequency, so we had to migrate to multi-cores. So you can see here that the number of cores increased. And we allowed many different things, right? The democratization of technology, PCs and smartphones everywhere, the birth of Internet of Things, like with IoT devices, applications starting in milliseconds rather than minutes. The guys who are a little bit older than this new generation know what is to wait for, let's say, any software, to open the computer, to start the computer, and to allow the really high-level language like Python, because the programmer became way more expensive than the machine. And then people started forgetting us because they took the hardware for granted, in the meaning that they supposed that we were able to deliver new hardware, faster hardware every year, as you used to do. And as you can see here, we were almost done, right? From 2015 until these days. So what happened? Well, the limits of generic instruction level parallelism and thread level parallelism, in the sense that, for instance, you could not develop way better superscalar processors, did not kick in the door, in the sense that the dinner predicted that the power would be constant with the increasing density of the transistors, but it happened that it also stopped. So now everybody knows what power and energy are, from the smartphones because of the battery life to the data centers because of the costs of the energy. And you have extremely expensive foundries, in the sense that it is really expensive to build a new foundry to project and build the newest hardware with the smallest possible transistors. But even so, we were years ahead of most application requirements. Regular people just don't need to buy new PCs, and you have like the new Batman and Robin, which are the multi-core processors and GPUs, right? Almost everybody was happy with that. The regular user didn't feel that he needed or she needed a new hardware to improve their applications. Of course, that were specific fields like gaming, for instance. You always need more frames per second. But then, deep and very, very, very deep neural networks happen, right? And remember that transformers weren't even a thing back 2020. And here you see actually the same line I've shown you. And here is the requirements for deep learning. So there is this gap. If you're old enough, you remember the memory gap between the processor and the memory, right? And now you have the hardware gap, because comparing the actual hardware that you have and the requirements that deep learning involves. And again, transformers weren't even a thing when this figure was built. But actually, the hardware flag was set in 2020 in this very, very interesting paper, which is called ImageNet Classification with Deep Convolutional Neural Networks, but it is more famous because of the author. In this paper, they proposed the AlexNet, which was like a huge step towards more accuracy with convolutional neural networks. And if you read the abstract of the paper, you'll see that they are mentioned GPUs, a very efficient GPU implementation of the convolutional operation, as a contribution of the paper. And if you open the paper, you take a look at the page, you see that all of our experiments suggest that our results can be improved simply by waiting for faster GPUs and bigger data sets. So at that time, GPUs, or the lack of hardware, was already a problem. So the flag was set. And this is an interview, you know this, Mark, right? And he says, energy not compute will be the #1 bottleneck to AI progress. He was mentioned that you can watch these, highly recommend to watching this interview on YouTube. There was a time that we had this problem with the supply chain of GPUs, but now companies are in doubt, are a little bit more cautious because of the cost of energy. For instance, energy is regulated by the government, so it's not all right to go to a small city and just consume like 20% of the whole energy that was supposed to go to that city. And if you think that it is not the reality, take a look at this chart here, and you see that right now Google and Microsoft, they consume more energy than small countries, and this is, of course, getting worse, right? So they remembered us again, and now you have to save them all. So how can we save the world? Or the summary of this talk, I will talk a little bit about the efficient hardware that you have to execute in an efficient way, or the best way we can, AI, some other optimizations, which are the newest Batman and Robin, and how can we play with these optimizations considering the IoT cloud continuum. Talk a really quickly about some case studies and the road ahead, the conclusions of this. One thing that we need to, actually two things. First is that all these images were generated using Microsoft Copilot, right? And the second one is that the basics of DNNs. And one thing that you need to keep in mind is that deep neural networks in general, they are basically matrix multiplications, right? So we have the weights, the inputs, the neural inputs, they are multiplied by each other. We sum up all of them together. There is an activation function, and then we move them forward through the neural network, but they are a matrix multiplication. Remember that flag that was set. So the efficient hardware to execute that, of course, the first type of efficient hardware are GPUs. And note that when NVIDIA came up with the idea of GPUs, which are general purpose GPUs, they didn't realize that they would actually AI would become the main market for them. Why is GPU so efficient? Because you see here you have the streaming processors, the CUDA cores. This figure was taken from the quantitative approach, the quantitative approach of Patterson and Hennessy, the famous one. And the most interesting part here is that you have one instruction that computes on different data, right? So it's a kind of single instruction mutable data, but actually it's single instruction mutable thread because each thread executes the very same instruction, but on different data. And you have a warp, which is a set of 32 of these instructions, same instruction. So in this case here, one instruction from one warp would take 4 cycles because have 8 CUDA cores. 8 plus 8 plus 8 plus 8, 4 cycles. But the secret here is that when the GPU finishes executing this instruction from one thread, it switches to another thread, to another instruction from another set of threads, another warp. And what does it do? It hides the memory latency. And you all know that the biggest problem of the von Neumann's architecture is the memory bottleneck. You need to fetch instruction, fetch data, and everything else. So the GPU is so good because it hides the memory latency. But pay attention to that. This only works if you have extremely parallel software to execute. And guess what? Matrix multiplication is exactly what any GPU needs. So you see, you have streaming multiprocessors increasing in number. You got that. Now you have extremely, massively parallel processors composed of thousands of CUDA cores that are able to execute things that are parallel, like matrix multiplications, and therefore deep neural networks. But the problem is that they are really power hungry, and they lack flexibility for model optimizations, as we will see later in this talk. So Google was and still is using GPUs, but they thought, look, we need to make this more efficient. So C, TPU is tensor processing unit. And they figure out that if user searched by voice for only 3 minutes a day, using speech recognition, again, ChatGPT wasn't a thing at that time, computation on Google's data centers would double. So they designed a new chip called TPU, which is, as you can see in this table, way more efficient in terms of power, throughput, and everything else than any CPU or GPU at that time, and it still is. So the ASIC was designed and verified in only 15 months, and it is the first ASIC produced by Google, designed by Google, right? And the interesting part is that it is very interesting. This is the how it works, and it is not in scale, but this is the heart of everything. So this is basically a matrix multiply unit with lots of functional units or execution units that only make multiplication and accumulation, right? And the secret is that instead of fetching the data and executing it using the regular functional unit, they did a different thing. They made the data flow through the hardware, right? So again, they are avoiding the von Neumann bottleneck. They are in their 4th version. But you see, what a new idea what a new idea. Actually, this is a systolic system. And it was proposed like 42 years ago. I was only 1 year old at that time. And the systolic architecture is that the memory is the heart, the data is the blood, and the processing elements are the cells. So the heart pumps the blood through the data, through the cells, right? And the TPU is like, it's some sort of rebirth of systolic architectures. Nobody had a use to it until now. But again, it still lacks flexibility, can only execute certain types of models, and it has a fixed data type. And then we have FPGAs. FPGAs and deep neural networks. So this is a really old figure comparing an FPGA with a Pentium 4. So this is really old. But the interesting part is that with FPGA, besides being reconfigurable, so we can quickly design and prototype any project, we have access to the latest feature size of transistors, the latest technologies, because Xilinx, for instance, has access to it, which is really hard nowadays. So if you talk about new proposals in terms of architectures to execute, to speed up the NNs, you see that most of them are FPGA-based, 64%, according to this survey, which is a really new survey, right? And even though this is specifically for FPGA, we can classify any sort of deep neural network accelerator according to this. Single engines, data flow, and full enrolled, which is a mix here. It's general purpose, but depending, it's not that efficient. And here is the opposite, right? So it depends on what you want. And let's take a look quickly at these different kinds of accelerators. So the single engine basically is like a systolic array like you've seen, or multiplier trees. And usually you have like these specific, let's say, coprocessor to execute very quickly these operations, right? And you have like different, as you can see here, some of them were discontinued, but they will still have like Xilinx VITS AI, for instance. It's a private IP. And then you have the data flow, which is very likely the most used one when it comes to FPGAs. And the FIN is the most famous one, also from Xilinx. And as you can see here, each layer is mapped to one or more processing elements in a forward fashion, right? So it's a single engine, but the accelerator is like tied to the model. So we have FIN, FPGA Convenet, HLS for ML, and so on. And finally, we have the fully enrolled. And the fully enrolled is really interesting because basically, and we have all of these, Xilinx again has all the kinds. But the idea is that you get 1 euro and you map directly to one lookup table. And as you can imagine, this doesn't scale very well, in the sense that they only support really small and simple neural networks, because even if you get a huge FPGA, you won't be able to map a huge neural network to that, right? And one thing that I need to mention, in of all these frameworks, they somehow try to bind, to tie the low-level framework, the hardware generation part, to some sort of non-framework like PyTorch, right? PyTorch is the most used one when it comes to hardware generation. So trying to bridge the gap between the designing of neural networks and the hardware design, right? So you can see some academic examples. And pretty fast, you have like this one, which is kind of a data flow diagonal, right? one of the most cited ones, and basically is an ASIC composed of these pieces that each layer is mapped to one of these pieces. You have IREs, which is very similar to the Google's TPU, as you can see here. And you have the bit fusion. The difference of bit fusion is that it is configurable in sense of the number of bits that you want to compute. This is very interesting for one specific type of optimization that we'll see in this talk. And you have other kind of stuffs like trying to use different technologies like memory stores with neural networks and matrix multiplication, which is really efficient because some of these technologies suits really well to operations like these multiplications. But of course that the GPUs or NVIDIA wouldn't stop, right? Seeing all this movement to improve neural networks. And let's start with another new word, let's say, which are tensors. In tensors, loosely speaking, vaguely speaking, is any multidimensional array of scalars. Some say that, okay, n equals 2, 3, 4, or tensor is anything more than 3 dimensions. So basically, tensor is a n-dimensional matrix, right? So what NVIDIA did, the NVIDIA, that's really interesting. NVIDIA designed tensor cores, and basically we'll take a look at that quickly, how it works. But basically, rather than spending transistors with CUDA cores, they added specific cores to execute tensors, to multiply tensors, basic matrix multiplication hardware with more dimensions. And for instance, the Volta, the first architecture, had 640 tensor cores. And basically, FP16, FP16, FP16. So this is the data type supported. And 12 times better than the Pascal on training, and 6 times better on inference. So what tensor actually does, it gets 2 inputs, multiply them, accumulate, and gives you the result. So rather than having the ability of, as old GPUs had to make 2-dimensional matrix multiplication, now we have the ability of doing multi-dimensional matrix multiplications, which is really, really impressive and really good for DNNs. And as you can see here, you have the warp processing, as I've shown you, and you have like a barrier. Then we call the tensor cores, and then we come back to the warp execution. And this is really interesting because I've been showing you different ways in hardware to execute the deep neural networks, and there is no tool, and there will be no tool automatic to decide which one you should use. And this is your problem, right? So you have to understand the model, you have to understand how it works, so you can find the best fit for your specific model, considering that you have restrict non-functional requirements like energy, performance, and area, and cost, and so on. This is the main challenge. So the 4th generation, which is the latest one, they have increased their peak performance by 60 times. And now they have like different data types, right? They are expanding their capacity of being customizable to different types of neural networks. And finally, what about CPUs? Oh, well, the truth is that CPUs are not very good for this kind of thing. Of course, that if you have small neural networks and you want to use them in your IoT device, maybe microcontrollers can be of some use. Intel has added some new instruction sets, instruction extensions to support basically multiply and accumulate, for instance, to improve a bit their execution. So in my point of view, CPUs are really good for small neural networks or those that will execute really quickly, and it isn't worth to offload the computation load to another harder piece, because there is a time to transfer the data to and from that the CPU or GPU or TPU or anything like that. And what we see in MP SOCs, we see that you have for instance, this is the Hexagon NPU. This is a Qualcomm processor. So you get the Qualcomm, you see there is a multiprocessor system on chip. It has several different components, and one of them is the neural processing unit, and basically it is their DSP, which is also a VLAW processor extended with a tensor unit. And again, what it does on different data types, very, very interesting, it does the tensor computation. It's very hard to find the internal hardware details of these tensor cores, right? But we know what they do. And they are exposed to the programmers through specific application APIs, through specific libraries. Well, but the truth is that the hardware alone will not suffice, right? So we need a Robin for our Batman, and we need model optimizations. So let's talk a bit about model optimizations here. How can we optimize the model? And in many times when you are trying to make things better, starting working at a higher level will bring better benefits than working at lowest possible levels, let's say transistors or layout, right? So you need to balance both. So the first one is quantization, and basically quantization is trying to represent rather using let's say decrease the resolution, right? So we have some curves here, you need to represent them with points. So of course that you are losing information, and the point is, let's say let me give you an example. Rather than using float pointing with 16 bits, we may use integer with 16 bits. The accuracy will drop, but the neural network will be really cheaper to implement. And you have two different types of quantization. The uniform, where we distribute the points evenly, considering the number of data, the amount of data we have, right? So the challenge here is find the right start and end point and how many points you use to represent that interval. And then you have the non-uniform, which is better because you're going to use more points to the parts that are more significant, but they are harder to implement. So usually you use the uniform one. Then you have pruning. And pruning, like the name says, is remove weights or neurons, and can be used also for CNNs, for instance, like channel pruning, you remove a whole channel. And pruning is really interesting because actually what you are doing to performing a lobotomy, right? And you have two kinds of pruning, the non-structured pruning, and as you can see here, we can remove any random part of the neural network, and it is better in terms of accuracy. So you can prune and it can train again, so the neural network will readapt to the lack of some neurons. So this is a process that works in a loop. And you see that there is this paper that showed that they could reduce the number of parameters of Alex, that the same one that I've shown you, by a factor of 9 times, without any accuracy loss, with similar results when using VGG16. So this is really interesting, right? But sparse matrix are a challenge, right? Take a look at this other paper here. And here is the original, the dense original one, the expected performance, because now you're removing parts of the neural network. And the sparse is actually executing it. And as you can see, in many times, or most of all the times, actually, the result on real executing on real hardware is not as the same as expected. Why is that? Because we added sparsity to our GPU. And sometimes the result is even worse than the original one. So you see, we cannot disconnect the model modifications and the hardware optimizations. And then you have structured pruning. And structured pruning is worse for the accuracy because you are removing, let's say, a whole layer or a channel. But the advantage of structured pruning, even though it is worse for accuracy, is that now we're removing a whole column or row of a matrix. So we're not adding sparsity. So you see here, we could remove 34 to 38% of performance improvements, improved performance, but close to original accuracy. So we had some sort of loss in accuracy. And it is important to mention that sometimes you take for granted like 1% of accuracy loss in neural networks. But when you are getting really near to 100%, 95, 96%, 1% is a huge amount. You need to double 5 times, 10 times larger, make it 10 times larger to achieve this small, quantitatively speaking, small number in terms of accuracy, right? And finally, you have dynamic optimizations. What are dynamic optimizations? Dynamic optimizations are those that somehow are performed at runtime. And one that's really interesting is early exit. In early exit, let's say you have 2 different inputs, the lion and the dog, who thinks is a lion. So, of course, that this one is easier to classify than this one, right? So you have like inputs that are harder to classify than other inputs. So the idea here is when you have a hard input, we make it go through the whole network. Oh, it's a dog. But if it is an easy input, we will use the early exit. So we already have enough features to classify that image. So we'll, of course, connect an extra exit layer to the neural network, right? And with that, we'll classify that it is a lion. So that input didn't need to go through the whole bunch of extra layers. So as you can see here, it is more expensive in terms of hardware transistor count, right? Because you need to add some extra layers. And the challenge is where to exit. So we usually measure the entropy, and basically is the level of confidence that you have for that image at a certain point. But it is actually pretty good. It can reach 2 to 6 times in terms of speedups in CPUs and GPUs. So this is a rather than in opposite to the quantization and pruning, this is a dynamic optimization in the sense that the decisions are taken at runtime, right? Well, now let's quickly discuss another thing that's really interesting. Which is the IoT cloud continuum. And I guess I don't need to convince you that you have like new smartwatches, now smart rings, and virtual reality, right? Companies are, going to this direction. You have like self-driving cars, have smart home, we have smart cities. This is really interesting. How, let's say, to improve the energy consumption of a city using the resources in a more efficient way. And you have like the environment, industry control. And what is happening that you are bringing, you are going to the opposite direction. You are bringing the computation load near to us. So you see, we may have the cloud, we may have some edge servers here. Imagine that you live, have an apartment, a set of apartments or houses, and may have like a let's say internal server for this group of houses or apartments, and we may have also an edge server in our house with the IoT devices. So this is the IoT cloud continuum, and the companies really are, the big companies are pushing us to compute with our devices, because they don't need to spend hardware nor energy for that. And this is another view. Some call this fog. So the nomenclature is not really well defined yet, but you have different layers, let's say this way, between us and the cloud. And like some years ago, we only had us and the cloud. So the challenge here is how to distribute this computation load, and of course the neural network execution, but because that's what is important today, through this cloud. So you may have different trade-offs in energy, latency, privacy, resource sharing, and cost. And the cost point of view may be different when we are considering ourselves or the cloud companies, right? So the challenge here is how to distribute this computation. Here is an interesting example. When it comes to learning, we may learn on device. So on device learning, we will have better privacy, we will have better latency, but I'm not sure about the cost. It depends. But the problem is that the training will be slower, but then you can have the collaborative learning, and you can distribute some parts of the learning throughout all the available devices. And finally, you may have what you have today most of the times, which is decentralized learning, in our case today, in the cloud. And we even may have like some collab zones that we know that in terms of privacy, we can trust them, or that they are suitable to exchange data, or they are suitable to exchange computation load, because many of them may not be compatible with each other. And here is a very interesting example, is that you get one application like vehicle to everything that involves different things like collision warning or traffic efficiency. And you see that within the same application, we will have different requirements, like different requirements in terms of latency or communication range or traffic type, which will force us to use different neural networks to execute on different hardware. And again, how to distribute this computation across all the hardware device available, this is a challenge. So I said before that we had one piece of hardware with many hardware components inside, and the challenge would be to distribute the computation across these devices. But now we have different pieces of hardware with different components distributed over a continuum composed of many different layers between us and the cloud. So, for instance, here, this is really interesting. You're using different neural networks with different configurations, with different domains, image classification and object detection. And you see that the CPU, the GPU, and the DSP will present different latencies. And of course, that the one important information missing here that is their accuracy. But you see that depending on the application you are going to use, you may not need the best possible accuracy. So you may use another model executing on a different hardware to get exactly what you need in terms of latency, but not only latency, in terms of energy, in terms of cost, and so on. And here you see what is important here is that you have different hardware executing different models in terms of operations per second and inference in float point operations per second. And you see that you have a really variation in terms of models and in terms of where you execute. But here, we're only saying one axis, which is the performance. But again, you have energy, you have power, have temperature, you have privacy, you have cost in terms of money, and many more. So this is a challenge, right? So what we've been doing, I'll quickly show you some case studies of our group. So the motivation here is that you may have different drones or cameras, right? And trying to detect people. And you see that all these cameras don't have enough processing power to the inference. So they're going to send the inference request to an edge server, which is in our case composed of an FPGA that executes FIN, the accelerator I've shown you. So we need to adapt to the edge server. The edge server needs to adapt to change in workload, because at a given point of time you may have a huge amount of cameras working together, but then a smallest number, and then can come back again to many cameras with many different requests. So what is the trick here? Okay, we want to track people even if you are going to lose a little bit in terms of quality and accuracy, right? So what we can do, we may have different versions of a model or different models, in this case, different versions of model using pruning. So you have models with different processing capabilities in terms of performance and accuracy. And our workflow, I'm not going to get into details here, but the static part of the workflow is performance design time, responsible for generating many different models, pruned models. And at runtime, you have a manager responsible for detecting the requirements of the application at that time. And as you can see here, we were able to produce a huge amount of different versions of the very same model with different costs in terms of BRAM, lookup tables, and flip-flops. And here you see that our flexible pruning is way better in terms of energy. This is just an example in energy. This is the original FIN, of course. You have two types of pruning, flexible one and fixed one. I've shown you just the fixed one. And you may navigate through all these models and get the one that best suits us at a given point of time, right? Another example is the 5G's automatic modulation classification, which we can use a DNN to classify the demodulation dynamically. So as you can see, now you are not only using pruning, but also quantization, using the same model. And as you can see here, here's the example using quantization, right? And also pruning, because you have less convolutional channels and neurons. So you have different models that were produced from quantization and pruning. And you can see here, you have different trade-offs in terms of power and, of course, LUTs and flip-flops and BRAMs and throughput, this is really interesting, and latency. And from that, we can, depending on the noise that you have, you may switch from the signal noise that you have may switch from one model to another. And you see that depending on where we are in terms of signal to noise ratio, the model won't matter. But as the signal gets different in terms of the quality of signal, now you have an interesting trade-off that you may explore and exploit at runtime. So the idea is to use simpler models when SNR is good and vice versa, right? So to finish this talk, what is the road ahead? So what you've been seeing in the last 1 or 2 years is basically ChatGPT, right? And all the derivatives. And they are based on transformers. And the problem is that, according to this source here, we have all these data. So the GPT-4 is huge, 1 trillion parameters, and needs multiple peta OPs to deliver responses. And you want them in less than a couple of seconds. So it was estimated that in 2022, Google search processed 3.3 trillion queries, the regular one, right? At a cost of 0.2 cents per query, in a total amount of 6.6 billion, the regular one, not the smart one. ChatGPT-3 would cost 3 cents per query. So on another, considering the same number of queries per second, 100 billion. And then you have ChatGPT-4. And ChatGPT-4, considering that you have to refresh the hardware every 3 years, it would cost daily, because of depreciation of hardware, 120 million per day. And with the energy cost of about 1 million per day. And here, while the regular Google search costs only 0.2 cents, the GPT-3 costs 3 cents, and GPT-4 costs more or less 10 cents. And that's really interesting because it only shows us that curve that I've shown you, comparing the hardware and the requirements of neural networks, the gap is only increasing. And we are the hardware guys. We need to try to figure out a way to solve this, right? But that's a problem. This is another interview between Bill Gates and Sam Altman, which is the CEO of OpenAI. And Bill Gates says that it blows my mind that we don't really understand encoding. And the Sam Altman says, I think we'll be able to understand these networks, but our current understanding is low. So you see, they built a model that they know that works, but they don't know exactly where to optimize it. The guys at the highest possible level of developing. And now they want us, the hardware guys, to optimize it without knowing exactly what parts are the most important ones. So that's a challenge. With that, I finish my talk. Thank you very much again.
Thank you, Antonio. So the audience, please, if you have any questions, do it using the chat channel as soon as possible. But waiting for some questions, I have one. So you talk a lot about CPUs, GPUs, and so on. So more generic processors. No? What do you think about in place of using a large set of CPUs and GPUs to have an architecture composed mainly by hardware accelerators? No?
I guess that the industry is moving towards this direction, but the problem is that it is very expensive, right, to design ASICs. And I guess that considering that to have a small number of foundries that are able to deliver such ASICs with the latest technology, that's a challenge. Google chose to balance between being generic and specific, but the truth is that we don't have ASICs yet. The thing that is more similar to ASICs that you find today are the NPUs that they have these specific tensor execution engines inside. But my opinion is that eventually we start, seeing more and more ASIC designs in the market because they are necessary.
Yeah, thank you. Just a comment about this. If you see some processor on chip like Apple ones that we have in our cell phones, half of the area of the chip is composed by hardware accelerators. No? So this
Yeah,
is
but
a great improvement in the reducing of low power consumption. No?
yeah, Apple is known for having the most these latest M processors. They are the most efficient ones, and the idea of this NPU that Apple uses very similar to the Qualcomm's idea. It's having like these tensor execution units. But yes, you take a look at the die of a chip today. It's amazing, right? The amount of hardware that it is spent for NPUs. You're right. Yeah.
Yeah. Yeah, there is a lot of interesting things to research and to improve, considering computer architecture that now is all in system on chips now. But I'm seeing no more questions here in the chat. So if someone still have a question, please do now. So if no, thanks a lot, Antonio, for the very interesting talk. And see you in person in near future, no?
Yeah.
But
Thank you very much again, Professor Hayes.
Before closing the session, just to remind you that you have a large set of other talks available in this YouTube channel, and that you still have till tomorrow. The submission system will be open for next edition of LASCAS, and together with LASCAS, we have IBER-CHIP, and IBER-CHIP, the call for paper is open till October 11. So thank you very much to everybody, and have a nice weekend.